What was learned previously in the two videos is all about the ideal gas law problems. Now, we'll be dealing with problems in regards to the combined gas law. Please note that these are different. The ideal gas law has its problems revolving around PV is equal to nRT formula. But for the combined gas law, it's basically PV over T is equal to PV over T. So what makes them different is the sub-value. Usually, the combined gas law deals with problems with condition 1 and condition 2. Like for this example, for this problem, a balloon gas has a volume of 106.0 liters when the temperature is 45 degrees Celsius and the temperature is 740 millimeters of mercury. What will be its volume? What will its volume be at 20 degrees Celsius and 780 mmHg pressure? So as you can see, there is scenario 1, scenario 2, condition 1, condition 2. So it's pretty obvious that that we're dealing with a problem that requires the formula of the combined gas law. We don't have the Roth's constant as well as the mole. We don't have that anymore. That's only existent with problems regarding the ideal gas law formula. Now, without further ado, let's proceed with the first question. Let's enlist EVT. All of them have sub 1, so that all falls for condition 1. V sub 2, V sub 2, T sub 2, they all fall for condition 2. So, for pressure 1, we have the pressure of 740 mmHg. For volume, we have 106 liters. For temperature, we have 45 degrees Celsius. For condition 2, what will the volume be? So what we're trying to find is V sub 2. We have 20 degrees Celsius and 780 mmHg of pressure. So for the conversion, we really have so many things to convert. As said earlier in the two videos before this, actually the first video before this, for pressure, the default unit is atmosphere, not mmHg. So as well, we have to convert the two temperatures. They have to be in Kelvin. Let's start with pressure 1. So pressure 1 is equivalent to 740 mmHg. Transfer it into atmosphere. 740 mmHg times 1 over 760 mmHg. You might ask why this is important. Well, you still have to note that 1 atmosphere is equivalent to 760 millimeters of mercury. So we multiply it this way and place it in the scientific calculator. 740 times 1 over 760, we get 0.97368. Please take note carefully, scrutinize them thoroughly. 42105. Now round it off to 5 significant units. 0.97368 atmosphere. This is our new value for P sub 1. For P sub 2, it seems that we lack space right now. Just make it uniform. There you go. For P sub 2, we have 780 mmHg. Turn it into atmosphere. 780 mmHg times 1 over 760 mmHg. Put all these in the calculator. Our answer will be, oops, sorry about that. our answer here will be 1.0263157889. So please double check. 1.0263157889. Alright, that is sure. Let's round it off to 5 significant units. 1.02632 atmosphere. So yes, we finished getting the pressure values. Let's move on to the temperature values. So T sub 1 is equivalent to 45 degrees Celsius. Turn it into Kelvin. For T sub 2, 23 degrees Celsius convert to Kelvin. Now, for temperature, again, Kelvin is equivalent to Celsius plus 273. Please note that. So 45 degrees Celsius plus 273, we get 380 in Kelvin. Now, for T sub 2, 20 degrees Celsius plus 273, our answer will be 293 Kelvin. Alright, we finished converting the values that are not in default unit. So let's move on to making the equation. So please remember the GRESA technique. So we have our given, then required. Next is equation, the E of GRESA. Equation, by the way, as I said earlier, ideal gas law formula PV is equal to nRT. They're different compared to the combined gas law. For the combined gas law, we have this. This is a screenshot from the previous video. We've discussed the corresponding formulas. So for the equation, what we're trying to find is V sub 2. So P sub 1, T sub 1 is equal to P V2 T sub 2. Just to make things a little easier, I won't be saying sub every time anymore. I'll just say P1 V1 T1 so that it will be easier to hear. So let's apply literal equations technique. For V sub 2, butterfly technique, move it that way. V sub 2 is equal to P1 V1 T2 over T1 P2. Now, let's start substituting the values already. For P sub 1, we have 0.97368 atmosphere times our volume sub 1 or volume 1. We have 106 liters. For temperature 2, we have 293 Kelvin. Now let's place a divide sign here. Then for T sub 1, we have 318 Kelvin times the pressure 2, which is this one. Let's just copy paste to make it faster. There you go. Alright, so that's pressure 2. Place all this in the calculator. I'll give you a few seconds to do it. Alright, I hope you've finished it already. Let's continue. V2 is equivalent to 92.65733.884. And V2, round it off to 5 significant units, 92.65734 liters. Now, let's check. Alright, that's correct. Right, we finished this problem. Let's move on to the second example. Practice question. If 10.0 liters of oxygen at STP, by the way, STP stands for standard temperature and pressure, which is this one. Please take note of that. Just change the highlight. Alright, are heated to 512 degrees Celsius, What would be the new volume of gas if the pressure is also increased to 1520 millimeters of mercury? Alright, so for oxygen, for condition 1, let's enlist the values. PVT, pressure, volume, temperature. There you go. Then for condition 1, we are given 10 liters oxygen heated to 512 degrees Celsius. New volume of gas if the pressure is also increased to give me a few seconds to consider this. So pressure 2 is 1520 millimeters of mercury, and for pressure at STP, that means standard temperature and pressure. We have to acknowledge that 512 degrees Celsius is supposed to be here because it says here 10 liters of oxygen at STP, so this is condition 1, are heated to 512 degrees Celsius. So this is the next temperature, heated to, and standard temperature pressure. That means temperature 1 is 273 Kelvin and our pressure is 1 atmosphere. And what we're trying to find is the new volume of gas, the new volume, which is V sub 2 or V2. Alright, we have to convert P sub 2 and T sub 2. Let's start with P sub 2, 1520 mmHg to atmosphere. So this is quite simple actually. 1520 mmHg times 1 over 760 mmHg. Our answer will be 2 atmosphere because 1520 divided by 760 is 2. So yeah, that's it for P sub 2. For T2, temperature 2, 512 degrees Celsius to Kelvin. Again, K is equivalent to degrees Celsius plus 273. So, 512 plus 273 is equivalent to 785 Kelvin. Now, with those values, we've stabilized all of the variables. They are now ready or prepared for the equation making. Let's move on to making the equation. We have to note again the combined gas law formula. This is the one. And yeah, let's proceed. PV over T is equivalent to PV over T. So this is condition 1, condition 2. And what we're trying to find is volume 2. Therefore, use the butterfly technique to remove everything that's with V sub 2 to make it alone. So P1 V1 T2 over T1 P2. V sub 2 is equivalent to 1 atmosphere times V sub 1 is 10 liters and our T sub 2, which is 785 Kelvin. Altogether divided by our T sub 1, which is 273 K. Then we multiply it with temperature 2. Pressure 2, which is 2 atmosphere. So give me a few seconds to check. Alright, yeah, everything's good so far. Let's simplify this into scientific calculator. We get 7,850 over 546, which is basically 14.3772838. Round it off, we get 14.37729. Yeah, 37729. Alright, liters, of course. Don't forget to place the unit. Alright, we finished. That's it for number 2. For number 3, I mean, we don't have number 3 for another example for combined gas law. In the next video, please expect that we'll be having chapter 3. It's all about Charles's law. This video talked about the combined gas law. Next will be Charles's law, and next will be Boyle's law. So yeah, that's everything for this video. Thank you for watching. I hope you've learned something today. Thank you.